Hello, pre-calculus students. I'm going to show you a couple things from 5.3a. Here's number 5, which is very much like 6 and somewhat like number 8, although number 8 is more like number 9. I'm going to show you number 9 too, but here's number 5. So you're taking the values that they provide for you of pi over 3 and 4 pi over 3, and we're checking to see what happens if I plug them in here for x. So I've got the equations written over here. So the tangent of pi over 3, I got to think about what that looks like. That looks like this. I got a 30, 60, 90 triangle going right here. This is root 3 over 2. And this is 1/2, which means the tangent is that one over that one, which is going to be just plain root 3. So then I end up with root 3 minus root 3 equals 0, and that's true. Okay, now how about 4 pi over 3? Well, it's the same triangle as this one, but it's in the position where 4 pi over 3. So that would be like this in the third quadrant. Now, the one thing that changes here is that I'm going to have a negative 1/2 and a negative root 3 over 2. So, but it'll still be the same relationship, and it's a negative over negative, so it's going to be a positive root 3 again. And positive root 3 minus root 3 again is 0, so that one also checks. Okay, so now let's look at number 9, which I've written here. I'm only going to do the first value, and you can do the second one on your own if you want to. The answer is in the back of the book. So I've replaced pi over 2 for x in both places. And so the sine of pi over 2, I'm going to think about where that is. That's on the y-axis right there. And the sine at that point is 1, because the sine is the y-coordinate. So I end up with 2 times 1 squared, and 1 squared is 1, so I end up with 2 there. And this one minus the sine of pi over 2. We already said that that's 1. So that's again 1 minus 1. So this is going to get me 2 minus 1 minus 1, which is 0. Checks. Works. Every one they give you that you're supposed to verify works. You know, these next two sections are basically the same idea. It's just that one of them focuses on the angle in degrees, the other one focuses on the angle in radians. So let's look at number 13. Number 13 is all I'm going to look at because the others are basically the same idea, just different specifics. So if the cosine of x is equal to negative root 2 over 2, I know that's a 45-degree triangle because I recognize that as going on the table for 45-degree angle for the cosine and the sine. The problem is I got to figure out which quadrants the cosine is negative. Well, all students take calculus tells me which ones they're positive. We don't want the positives, we want the negatives for the cosine, so that's going to be here. A 45-degree angle there, and another one there. So that would be 3 pi over 4 and 5 pi over 4. And you can check the back of the book to make sure I know what I'm talking about. But those are the two answers that we're looking for number 13. Now these directions are a little deceptive. It only says solve the equation. That implies that you'd solve it completely, meaning tell me every solution, which any solution means I'm not restricting the domain. It can be anything. So we'll take a look at one of these. How about number 31, which is actually pretty straightforward. So be sure you read the notes that are in the book. Number 31 says root 3 times the cosecant of x minus 2 equals 0. Now, the first thing I want to do is get the cosecant by itself. So I'm going to add 2 to both sides, which gets me root 3 cosecant x equals 2. And now I'm going to divide both sides by root 3. So I get cosecant x is equal to 2 over root 3. Now I don't have the cosecant memorized as well as I do its reciprocal function. Its reciprocal function is the sine. So that means the sine would have to be the reciprocal of this, which is going to give me root 3 over 2, which I instantly recognize that is a 60-degree angle. So we get a 60-degree angle going here. And with this being root 3 over 2, this angle right here has to be pi over 3. So x is equal to pi over 3. But there's also another place that the sign is positive, and that's in quadrant 2. So the same kind of triangle would go right there. And still got root 3 over 2 on the opposite side. So it's also 2 pi over 3. But the book is being unspecific on purpose. It wants you to generalize. So give me a general rule. So in this case, we'd say x equals pi over 3 plus whatever the period of the sine is. The period of the sine is 2 pi. So we're going to say 2 pi times n, but we like to put the n in here. And n stands for an integer. So it could be 1, could be -1, could be 2, 3, 5, 7, any of those numbers. But that tells me half of all of the solutions. The other half has to do with this, which looks just like this one, except it says 2 pi over 3 to begin with. And there's no way to shortcut this because these two things are not very easily identified by coming up with a general rule. So 2n pi, there we go. So that's our general answer, very generalized. And now I'd like to get to .35, and while I'm doing 35, I'm going to have to think about how to isolate the variable. Right now, it's kind of isolated already. And we're going to use the product property, the zero product property, to solve this problem. Now, if I've got an A times a B, and A times a B is equal to 0, either A is equal to 0 or B is equal to 0 or both. So let's solve this one. Well, if x is equal to 0 would have to be one of the solutions. Now, is there another place where the sign would be equal to 0? And the answer to that is yes. It would also be 0 wherever the y coordinate was 0. So it would also be 0 at pi. Now this one I'm going to solve by subtracting that -1 over. I get sine of x is equal to -1. I got to think about when that happens. Well, that only happens when x is upside down, so that would be in between quadrants 3 and 4. So I believe it would be 3 pi over 2. And there's our 3 solutions. Okay, finally, I've got 2 more to do. We're going to look at 43 and then 51. 43 has this very complicated looking equation. Well, we learned by reading the notes in the book that I don't ever want to divide both sides by something. I want to subtract it over and factor. And that's, in fact, the approved way to do that. So if I have the sine of x, the first thing I'm going to want to do is subtract 3 cosine x so that it's on the other side. So I'm going to get sine of x, cosine of x, minus 3 cosine of x. Now what I notice here is that there's two terms, 1 and 2, and they both have a cosine x in common. So I'm going to factor out that common factor of cosine x. Well, that leaves me with the sine of x minus 3. Now either this is equal to 0 or that's equal to 0, and in this case we're going to assume that they're both. So cosine x equals 0, or sine x minus 3 equals 0. Now in this case, when is the cosine equals 0? Well, it's whenever the x value is equal to 0. So I believe that would happen here and here. So that means x is either pi over 2 or 3 pi over 2. Now on this one, I actually need a calculator, so I'm going to hit sine of x is equal to 3. Well, wait a minute. Sine can't be more than 3, so this part has no solution. And that happens when you've got factoring going on like this. Sometimes one of the factors is nonsense. Well, we still did get two answers out of this, pi over 2 and 3 pi over 2. Okay, one more example, and that has to do with 50 and 52. It says, use a graphing utility to approximate solutions. And then by collecting all terms on one side, graphing the new equation, and using the zero root feature to approximate the x-intercepts of the graph. Now, 51 looks like this. And I would argue I can actually solve this algebraically. And you can too, but you're not required to, not according to the book. So the first thing I want to do is make it all about cosine, since the sine squared can easily be replaced with 1 minus cosine. So I get 4 times 1 minus cosine squared of x equals 2 cosine x plus 1. Now I'm going to do what the book suggested, which is move the whole thing over. And so I get 4 minus 4 cosine squared x minus 2 cosine x minus 1. Now I notice we got some like terms here, negative 1 and a positive 4. So that would give me 3. And let's put it in descending order. Minus 2 cosine x minus 4 cosine squared of x. Now whenever you have a situation like this, and you suspect it can factor, you can always rewrite the problem and see if the factors come to you. In this case, it'd be 3 minus 2x minus 4x squared equals 0. Well, as it turns out, this one doesn't factor, so I don't think it's going to solve algebraically very easily. But I can do what the book suggested. Let's go back to this. And I'm going to slide down here, and I'm going to put 4 sine squared. So I'd like to move this all over to one side. So I'm going to subtract that 2 cosine. I get 4 sine squared x minus 2 cosine x minus 1 equals 0. And now I'm going to break out my Desmos. And I'm going to insert in that graph, which is 4 sine caret to make it move up squared x minus 2 cosine x minus 1. And now it asked me specifically to solve it between, well, let's go back to that and see what the instructions say. Between 0 and 2 pi not include 0 is. So if I go to look at that graph, I'm going to tell it to create the x-axis in terms of pi, and that'll make it a little easier to see where 2 pi starts and where it ends. So it looks like we've got 4 solutions. That one, that one, that one, and that one. And that's what I would write down. Some nice symmetry going on there. This one's a positive, 8.861. This one's a negative. And likewise, this one's a negative and that one's a positive. So that's it for my help on 5.3a. If you have any specific questions, just email me at dmedic@tusd.net and I will respond.